Hello. In today's lecture, we're going to be starting off with second order differential equations. So next week, Wednesday, we're going to be using part of the tutorial time as a lecture where we will continue with the second order differential equations, and then the remaining time will be the tutorial, again on second order differential equations. Okay, but I just want to go through a brief introduction on the method to solve these equations. Okay, so second order differential equations. Okay, so the type of equations that we're going to be looking at first are called homogeneous second order differential equations with constant coefficients. So we have AY double prime plus BY prime plus CY is equal to 0. Okay, so A, B, and C, those are our constant coefficients. And the fact that the right-hand side here is 0 means that this is homogeneous. If the right-hand side is some function of x, then we say that it is inhomogeneous, and we'll be dealing with that later. Okay, we do have second-order differential equations where instead of constant coefficients, we have functional coefficients. However, we won't be dealing with that in this course. Okay, so how do we solve this? So what we do is we make a guess or an educated guess at a solution of the form y equals e to the lambda x. Okay, so we guess that this is a solution to this equation. And a little homework exercise, why is this a good guess? Okay, so you can think about why this would be a good starting point at finding solutions. Okay, so with this idea in mind of y equals e to the lambda x, let's substitute this in and see if we can solve for this unknown lambda. So we're going to get a, e to the lambda x double prime, plus b, e to the lambda x prime, plus c, e to the lambda x. And this is equal to 0. Now, taking the second derivative means we take down lambda twice. So it's going to be a lambda squared, e to the lambda x, plus b lambda e to the lambda x, plus c e to the lambda x is equal to 0. Now, this e to the lambda x that's been repeated, we can divide through by that, and thus canceling it. So we're left with a lambda squared plus b lambda plus c is equal to 0. This is called the characteristic polynomial. Characteristic polynomial. And it's quadratic because we had a second order differential equation. This can be solved for lambda using the quadratic formula. And we get lambda is equal to minus b plus minus the square root b squared minus 4ac all over 2a. Now, depending on that discriminant, b squared minus 4ac, we have 3 possibilities for this lambda value. So let's say 3 cases. So number 1, we can have 2 real roots. Yeah, that's if the discriminant is greater than 0. We can have 1 real root if the discriminant is equal to 0. And number 3, we can have 2 complex roots if the discriminant is less than 0. Okay, so let's go through these cases one by one to see what happens to our solution. Okay, so in the first case with 2 real roots, so number 1, 2 real roots. This is when we have lambda 1 and lambda 2. Okay, and they're both real. Since we have two of them, both of them would be a solution, right? But since we've got two of them, we can write the solution as a linear combination of the two possible solutions. The reason we can do that is because the original equation is linear, because the derivative is linear. Okay, so we can take our two possible solutions, the one with lambda 1 and the one with lambda 2, and write the solution as a linear combination. So we have y is equal to a1 e to the lambda 1x, that's a valid solution, but a2 e to the lambda 2x is also a solution, so the sum of them is again a solution. Okay, so this is the most general form that we can have. And notice that we have two unknowns here, a1 and a2. So when we did first order differential equations, we had one unknown, our integration constant, the plus c. Here we have two unknowns for the second order differential equation. Okay, we'll see that's in general. So for a given second order differential equation, you're going to have two unknowns. Okay, then number two, if we have a single real root, lambda, so now the solution is going to be y is equal to a e to the lambda x. However, we can't just have one solution like this, because you can think of the solution space as two-dimensional, like a two-dimensional vector space. So we need two independent solutions to span the two-dimensional space. And the way that we do that is by adding an extra term plus a 2x e to the lambda x. Okay, so these are independent and they span the solution space. Okay, maybe we can leave that for homework. So if we treat these as vectors in a vector space, homework, show that these are independent. Okay, and if you're a bit stuck with that, I have a hint. Look at the Wronskian. Okay, so that's just a little hint to help you with that. Okay, so we want to show that these two solutions are independent and they span the solution space. Okay, and then if you're stuck, look up what the Wronskian is. Okay, that should help you out. Okay, so that is if we have a single real root. The last case is if we have two complex roots. So number 3, two complex roots. So in this case, we can write the lambda as alpha plus or minus r beta. Okay, so we have one complex root, and then the other complex root will be the complex conjugate of it. Okay, so since we have two roots here, we can write the solution as we did for the first case with the lambda 1 and the lambda 2, and let's see what we get. So y is equal to a1 e to the alpha plus r beta x plus a2 e to the alpha minus r beta x. Now we can simplify this some more. We can write this as a1 e to the alpha x times e to the r beta x plus a2 e to the alpha x times e to the minus r beta x. Now this e to the alpha x we can take out. So we have e to the alpha x into a1 e to the r beta x plus a2 e to the minus r beta x. Now we can use Euler's formula to write those two terms in terms of sine and cosine, which is a bit easier to work with. So we have e to the alpha x, a1 cos beta x plus a1 sine beta x plus a2 cos beta x plus a2, minus a2 sine beta x. Okay, we can collect some like terms together. So we get e to the alpha x, a1 plus a2 cos beta x, plus, we have r here, and we have an r here. So plus r a1 minus a2 sine beta x. Okay, now instead of a1 and a2 with the sum and this difference, since those are just constants, we can define new constants to make this a bit easier. So we write this as e to the alpha x. Let's call the sum b1 cos beta x plus, and let's call this other constant, the difference times r, let's call that b2. Okay, so this gives us an alternate form without those imaginary parts. Yeah, so e to the alpha x, that's from the real part, and then the cos beta x and sine beta x, that's from the imaginary part. Yeah, from our complex lambda. Okay, so this is the general methods to solve homogeneous differential equations. So that is with this right-hand side being 0. So that makes it homogeneous. Now we're going to take a look at the inhomogeneous case where the right-hand side is not 0. Okay, so inhomogeneous second-order differential equations. Okay, so these have the form ay double prime plus by prime plus cy is equal to f of x, where that is some function of x. Okay, so it's no longer 0. Okay, but we're still working with constant coefficients. So a, b, c, those are just constants like before. Okay, so the way that we solve this is in 2 steps. Okay, so there's 2 steps for this. Okay, so the first step is to consider ay double prime plus by prime plus cy is equal to 0. Okay, so we ignore the f of x for this particular case here, and we just assume that the equation is equal to 0. Okay, so for the first step, we ignore that right-hand side. And we solve it as if we were just given this homogeneous case. So solve this as before, and call the solution yc. We call this the characteristic solution. Okay, so that's step 1. We ignore the function, so we just assume the right-hand side is 0, and then that solution is called the characteristic solution. Now, for the second step, we look at the form of f of x, and whatever that functional form is, we assume a general form and call that the particular solution. So let yp for the particular solution be a general form of f of x. Okay, so what do we mean by a general form? Well, the best way to understand that is to look at some examples. So if f of x is equal to 1 plus 2x, in other words, it's just a linear function, then yp will take the form a plus bx, where a and b are unknown. So if the function is linear, then we assume a general linear function. So a and b are unknown. If the function is quadratic, so we have, for example, 1 plus x minus x squared, then for the particular solution, we also assume a general quadratic. So a plus bx plus c x squared. And in general, for any polynomial f, we assume a particular solution yp that is also the same degree polynomial, okay, with the unknown coefficients like we have here. Okay, we could also have trig functions. For example, if we have cos kx, then for the particular solution, we assume a linear combination of cos and sine. The reason we assume a linear combination is because when we take derivatives of sine and cosine, they turn into each other. So we can't just take one, because with the derivative, the sine turns into cosine, the cosine turns into sine, so we need to have both. However, this term k, that is fixed. So we have a cos kx plus b sine kx. Okay, the k is fixed in both cases here. Okay, similar with an exponential. Let's say we have f of x equals e to the kx. Then the particular solution will be a e to the kx. Again, the k is fixed in both cases, but the constant a, that's unknown. Okay, and then lastly, we can have a combination of things. So let's say we have a combination of a polynomial times an exponential. Well, now we just combine the particular solutions for both of those. So since we've got a polynomial x squared, we're going to have a general polynomial a plus bx plus c x squared. And the general form for e to the kx is some constant a times e to the kx, but that constant can be absorbed into this first part with the a, b, and c. So we can just write e to the kx. Yeah, and you do that in general. So you build up your particular solution from whatever the function is, and we generalize it with these coefficients. Okay, so how do we then solve for the coefficients? We can solve for these unknown coefficients by substituting our particular solution. So substituting yp into the left-hand side of the differential equation. So the one with the ay double prime plus by prime plus cy. So we substitute that. So substitute into the left-hand side and compare both sides. Okay, so comparing the left-hand side to the right-hand side, we can then identify what those coefficients have to be. Yeah, in other words, substituting in, we get a y p double prime plus b y p prime plus c y p is equal to f of x. Yeah, and then since yp is chosen to have the same form as f, the left-hand side and the right-hand side will also have the same form. And then from that, we can just compare coefficients and solve for whichever coefficients are unknown. Okay, so that gives us our particular solution. Finally, our final solution, y, is going to be the characteristic solution plus the particular solution. And remember that the characteristic solution will still have those unknowns. So where this was equal to 0, we had the sum of two terms with two unknowns. We're going to have that as well here. So the coefficients for yp, those are found. We know what those are. However, we still have the unknowns from that. And we can solve for those unknowns given two initial conditions. So we can solve for the remaining unknowns given two initial conditions. Okay, so this can be the function evaluated at 0, for example, and the first derivative evaluated at 0. Okay, so we call those initial conditions or boundary conditions. Yeah, but that depends on the problem at hand. So for boundary conditions, we might be given y0 and maybe y1, for example. And then from those two conditions, so fixing y at 0, fixing y at 1, we can use that to determine those remaining unknowns. Okay, so it can either be via initial conditions, so y at 0 and the derivative at 0, or boundary conditions where we are given y at either endpoint. Okay, so in this case, y at 0, y at 1. Okay, so that is a brief introduction to second order differential equations. We will continue with examples on Wednesday morning. Please remember that the time has been shifted. Okay, so we will start the tutorial a bit later. So we start with the lecture, and then we will have the tutorial after that. Okay, and then again on the Wednesday, I will hand back your tests. Yeah, so then you can have a look at that. Okay, but as always, if you have any issues, please just email me or you can visit me in my office. Just send me an email before, just to check for my availability. Okay, I'll see you next Wednesday.